The space shuttle is in orbit, and members of a highly specialized team at NASA's Ames Dryden Flight Research Facility are tracking its progress. In 2 days, the orbiter will re-enter Earth's atmosphere over the Indian Ocean. It'll perform an intricate series of slowing maneuvers and glide to a successful landing at Edwards Air Force Base.
Okay, Houston, we're rolling out on final, and it looks beautiful. Roger, Joe, we copy. Your winds are 250 at 17, gusting to 21. Roger that.
Range 12,000 feet. The gear's down, altitude 300 feet. Just 800 feet from the end of the runway. And the main gear are down. Nose gear is securely down. A touchdown at mission elapsed time of 6 days, 56 minutes, 4 seconds. Nose gear down at 6 days, 56 minutes, 16 seconds.
Edwards is the home of NASA's Ames Dryden Flight Research Facility, the nerve center of 3 sites supporting a highly evolved technology network called the Western Aeronautical Test Range. The range is a key facility in NASA's aeronautical and space research and a major national resource. Its development is a critical achievement in flight testing today's experimental aircraft. The range furnished precision monitoring for the orbiter during its crucial end-of-mission maneuvers and helped it guide the ship to a safe landing. The first sonic boom was heard at Dryden on October 14, 1947, when Chuck Yeager flew the X-1 experimental rocket-powered airplane through the sound barrier. Facilities and equipment for air-to-ground monitoring of test flights were primitive. Flight research results depended mainly on air-to-air chase observations and recording data on board for later examination. In 1959, NASA began testing the X-15 rocket plane. This air-launched, highly experimental test vehicle reached altitudes far outside the atmosphere and flew at unprecedented speeds. No chase plane could keep up with it. Testing the X-15 absolutely depended on immediate, sophisticated air-to-ground communications, tracking, and data acquisition. Unlike previous research aircraft, the X-15, with its high energy management requirements, demanded real-time tracking and voice communication to accomplish its mission. To test the X-15, Dryden engineers developed a complex system for flight monitoring. A system that went far beyond anything yet known. They called it the X-15 High Range. The range allowed researchers on the ground to track the X-15 throughout its entire mission, monitor its data during flight, and maintain radio contact with the pilot. It enabled investigators to deal with data in real time during experimental flights and change plans during flight. This greatly increased each mission's effectiveness and saved time and program cost. It also made flight testing safer. Dryden engineering teams set up remote sites at Ely and Beatty, Nevada, to accommodate the great speeds of the X-15. For testing high-speed, long-range aircraft, Ely and Beatty became outer perimeters of the high range. The Western Aeronautical Test Range of today is the high range grown up, a working integration of state-of-the-art communications, tracking equipment, computers, and electronic display systems. The result of creative engineering proven by continuous application. These systems provide the laboratory needed to test today's high-performance air and spacecraft. The Mission Control Center is the focal point of the range. This is where everything comes together. Here, supremely advanced systems such as the Master Graphics Interactive Console or Magic Display give researchers a unique edge in flight testing. Magic is an interactive, high-resolution, easy-to-use tool which allows investigators to see yaw roll, time history, and cross plots on command It opens new capabilities in changing parameters during flight, thus saving valuable time and optimizing information yield. Here, the Real-Time Interactive Map, or RIM, is helping advance flight research. This is an intelligent graphic workstation that instantly shows an aircraft's flight position with respect to geographic location. RIM tracks, displays, and computes time-distance measurements, functions done previously with pen and paper. It immediately projects flight path on command, allows the controller to change perspective by zooming in on areas of interest, and warns the flight controller when his aircraft is approaching a restricted area. RIM reduces workload on the host computer, which is freed to perform other critical mission-related tasks more efficiently. The F-18 High Alpha Spin display demonstrates how innovative graphics systems can be tailored to meet requirements of a specific program. This presentation details precisely and in real time such critical information as yaw rate, airspeed, altitude, and spin conditions for high-risk flight research programs. Such advanced systems greatly simplify the work of the range control officer, whose job it is to determine how well the range is operating. They vastly increase findings of the principal investigator and his team during a mission, and the quantity and quality of work achieved by the flight controller, who coordinates the test aircraft, chase plane, and control tower. They enhance flight safety monitoring and the capabilities of the aircraft operations director and flight safety officer. The output of all mission control systems depends on data drawn in real time from all other elements of the range: the aeronautical tracking facilities, the communications building, the real-time processing, and display systems. Dryden has 2 tracking facilities. Their antenna systems provide radar and telemetry for command uplink and downlink research data. Their equipment can track local test flights or satellites orbiting at altitudes exceeding 32,000 miles. During space shuttle missions, support technicians use the facilities to track the shuttle in orbit and during re-entry. These stations are the acquisition points for all research data from air and spacecraft, and the points for primary command uplink. The communications building provides the radio frequency link, which allows aircraft and spacecraft to talk to ground control. It provides air-to-ground communication between pilots and engineers in all of a mission's participating aircraft, and backup command uplink to research vehicles. The telemetry processing room houses many of the range's real-time processing and display systems. Today's high-performance test aircraft produce such huge quantities of data that human investigators working on their own can't begin to interpret and use them during a mission. These systems rely on computers for quick real-time processing and conversion of raw data into real-time information that researchers and pilots can respond to during a flight. The real-time processing and display systems generate organized results on control room monitors and strip chart recorders. A vital part of today's Western Aeronautical Test Range is the Moffett Flight Complex in Northern California. Based at Ames Research Center on Naval Air Station Moffett Field, this is one of the country's prime test sites for powered lift and rotorcraft vehicles. A new satellite link, the NASCOM Integrated System Digital Network, generally shortened to NISDN, and a process called Time Division Multiple Access allow Moffett and Dryden each to monitor flights at the other's facility and at their remote locations. Because the area surrounding Moffett Field has grown increasingly congested, researchers here conduct many of their sea-level altitude tests at Crow's Landing in the San Joaquin Valley. While Crow's Landing is equipped to support these flight tests, much of the real-time monitoring and post-mission processing is done from Moffett Field. Range versatility is giving researchers vast new capabilities and opening great new vistas in research flight testing. At the same time, sophisticated new research projects are demanding new capabilities of the range. There is a growing need to test experimental aircraft at remote locations. Engineers have answered this need by developing the Mobile Research Flight Test Support capability, generally known as the Western Aeronautical Test Range Mobile System. Created for total adaptability, the mobile system can go virtually anywhere and get to work immediately on arrival. Its air ride suspension protects the delicate equipment inside during hauling, either over ground or by air. Its first run, supporting the Advanced Fighter Technology Integration F-16 in tests at Nellis Air Force Base, proved completely successful and demonstrated that it can handle real-time processing and display and communications with the airplane and mission control at Dryden. An outstanding example of resourceful design, the fully equipped trailer can perform all of the functions normally done in the control room at Moffett or Dryden. Its approximately 2,600 cubic feet can store the 6-foot telemetry antenna during moves. When the trailer arrives at a test site, expandable 18-foot sections on either side of the computer banks open to provide 630 additional cubic feet of space. Highly compact computer banks receive, store, and process data for the trailer's major components: telemetry, communications, real-time and post-mission processing, display and strip charts, and a full remotely piloted research vehicle cockpit, which permits remote operation of an unmanned aircraft. The trailer can operate independently or interface with a mission control center. Because it is highly automated, 2 people can handle operations and maintenance. The trailer's reinforced roof supports the deployed directional antenna, which accommodates both tracking and communications. The antenna can receive and transmit in the L, S, and C bands. When the trailer reaches its full capability, the system will include a mobile earth station, radar system, and frequency van. Heavily dependent on the range and the mobile trailer is the Joint Army-NASA Rotor Airloads program. This project is using a Black Hawk and other helicopters to discover what stresses rotor blades encounter during flight. Researchers will measure a total of 250 pressure points on the blades. All of these measurements require extreme precision and real-time transmission to both ground control and a tape recorder on board. This places enormous demands on range equipment. Requirements for acoustical testing and a variety of flight modes call for flying in different locations, including Edwards and Crow's Landing. Ground instrumentation for these flights is program dedicated, very costly, and not practical to install in all control rooms. The mobile trailer allows researchers to make a single installation, which they can move from one location to another. Ames researchers are using Crow's Landing to conduct tests with the Harrier. This remarkable aircraft flies successfully both as a vertical takeoff vehicle and as a high-performance fighter. Investigators are using it to explore flight dynamics, propulsion, controls, and display for short and vertical takeoff and landing vehicles. They expect these tests to result in advanced design concepts for aircraft of the future. Harrier flights generate a great amount of information and rely heavily on range data acquisition facilities. The range has been indispensable in supporting this uniquely versatile aircraft called the tilt rotor. Nacelles mounted on its wings tilt upward to make it fly like a helicopter, or 90 degrees forward, allowing it to fly like an airplane. With the tilt rotor, Ames Research has produced an extremely successful working aircraft from which the Marine Corps production tilt rotor V-22 was derived. Dryden is where Ames tests high-performance airplanes. Clean, dry desert air and sparsely populated terrain make this location ideal for researching high-speed jet and rocket-powered aircraft. The F-18 High Alpha research vehicle is pushing high performance to unprecedented extremes. Using a modified pre-production F-18 as test bed, this program is working to improve fighter performance at high angles of attack. This is possible only if engineers learn precisely how air vortices flow during high-angle maneuvers, both on and off the airplane's surface. To study on-surface flows, investigators released colored dye during specific maneuvers over areas of interest, such as the nose and wing, and photographed the resulting patterns. This information also is downlinked in real time for immediate assessment. Off-surface flows show up clearly when an onboard generator emits smoke over the F-18's leading edge extension, a video camera in a nearby chase plane, and another inside the F-18 showing precise vortex flows. The airplane carries a total of 4 strategically placed onboard video cameras. This program is completely dependent on the range. During test flights, the F-18 downlinks 2 video signals and 2 streams of telemetry data. It depends on the range's command uplink capability for trajectory guidance. The program's specific high-alpha spin display is critical to carrying out F-18 missions, since it defines emergency recovery procedures for any loss of control situation that might occur. The F-15 places enormous real-time computation and display demands on the range because its engine is heavily loaded with instrumentation. Researchers are using the F-15 to develop methods for reducing pilot workload. If they can create systems that take over basic operating tasks, pilots will be freed for other critical activities, such as responding to threats or setting up weapons systems. The program team is working on developing a trajectory guidance system. A computer which they have mounted in the airplane's ammunition bay calculates airspeed and altitude with no assistance from the pilot. Aircraft and engine command then can be supplied either to the pilot through the heads-up display or directly to the aircraft in the automatic mode. This technology significantly reduces pilot workload. The range, with its Magic and RIM displays, is uniquely equipped to support this program. These advanced interactive displays allow F-15 team members to view in real time the airplane's trajectory 3 miles behind and 7 ahead of its present position. At the same time, they also can watch the aircraft's ground track with reference to restricted areas and monitor processed parameters critical to the flight. Should any fault or failure occur on board, these displays will flag it immediately. The Advanced Fighter Technology Integration, called AFTI F-16, is another demanding program that puts extremely heavy loads on the range. AFTI is a joint NASA Air Force program. The aircraft, a highly modified version of the F-16 Fighting Falcon, has been expanding the limits of flight since 1981. Equipped with a unique set of computer-driven control surfaces, the AFTI can execute maneuvers impossible with any other aircraft. AFTI's total dependence on computers and experimentation with flight modes never before attempted make the range a crucial part of testing this airplane. A heads-up display, which superimposes critical flight data over the cockpit window, allows the pilot to monitor instrumentation readings without looking away from the flight path. Range tracking facilities simultaneously feed this picture to researchers in the control room, allowing them to monitor in real time what the pilot is seeing. Currently, the F-16, working to improve close air support in Europe, is checking technologies such as automated attack, digital map systems for poor weather and night flying, and target acquisition from ground control. This testing, utilizing computer-based artificial intelligence, uses great amounts of data and requires the capacity to profit from in-flight corrections and change the test agenda. The range gives AFTI critical support which is not available anywhere else. Its systems during flight offer more processed data in easily used form. RIM figures importantly by letting flight controllers reprogram for restricted altitudes. AFTI's multiple program requirements and exacting test schedule demand optimal return from test flights, and the range makes this possible effectively and safely. Some of the flight experimentation performed at Dryden has been so hazardous that researchers ruled out the use of onboard pilots. For these high-risk programs, they developed remotely piloted research vehicles, called RPRVs. The spin research vehicle was a characteristic RPRV. It was carried aloft under the wing of a B-52, then air-launched. Typical of all air-launched vehicles, RPRVs require precise coordination of carrier, test aircraft, and chase plane. They consume enormous quantities of range support. Pilots fly remotely piloted research vehicles from cockpits on the ground, depending completely on telemetry provided by the range to receive sensory information from and send commands to the airplane. The range's advanced antenna systems supply the primary command uplink to all of the RPRVs. The complexity of flight maneuvers accommodated by this impressive system was demonstrated dramatically in the testing of HIMAT. Short for highly maneuverable aircraft technology, HIMAT was one of Dryden's most spectacular RPRVs. At about 3,400 pounds and less than half the size of an average fighter, it allowed testing of a highly experimental configuration at considerably less cost than would have been the case with a man-rated vehicle. HIMAT was designed to be more maneuverable than any existing fighter and made turns pulling up to 8.5 times the force of Earth's gravity. Such maneuvers would cause extreme discomfort to even an experienced test pilot. The range antenna systems, with their enormous capacity, enabled the pilot to perform even the most complicated maneuvers from his ground cockpit. Its small size and quick movements made HIMAT very hard to track with conventional chase aircraft. Range tracking, telemetry, and command uplink made these flights possible. The most dramatic use of command uplink was the full-scale transport-controlled impact demonstration, RPRV, called SID for short. Dryden conducted the SID experiment in cooperation with the FAA and NASA Langley to test the effectiveness of crash-worthy advances, including an anti-misting fuel designed to reduce damage from fire following a crash. Researchers instrumented this old B-720 passenger jetliner to be flown as a remotely piloted vehicle. Pilot Fitz Fulton worked for months in the ground cockpit and in the plane itself with range support to prepare the jetliner's remotely controlled systems for its flight to final impact. During the crash test, range telemetry worked flawlessly. While best known for carrying out research on high-performance aircraft, Dryden's range has supported a wide variety of test aircraft, such as the Gossamer Albatross, which was pedaled somewhat like a bicycle. The Light Eagle, another human-powered experimental airplane, won 4 records during its range-supported flight tests. This aircraft was a Massachusetts Institute of Technology student project. The idea came from Greek mythology accounts of Daedalus' effort to build wings for human flight. The Eagle served as a prototype for the aircraft Daedalus, which flew the 74-mile distance from Crete to Santorini in a record-setting 3 hours 55 minutes. Dryden engineers supported the Eagle flight tests with long-range optics and a video van. To support development of the space shuttle, Dryden researchers built and tested a series of wingless aircraft called lifting bodies. The X-24B was one of these aircraft. They drew their lift entirely from their body shapes, which acted like the wings of conventional airplanes. The X-24B was rocket-powered, so it could reach speeds and altitudes similar to those encountered by the shuttle when it approaches to land. The lifting bodies depended on range support for energy management and guidance to the landing site. The uniquely configured X-29A forward-swept wing is entirely dependent on the range to conduct its flight tests. This high-performance research aircraft maneuvers at very high speeds. At the same time, it requires constant computer adjustment and correction to position its exotic flight control surfaces. The X-29 set a whole new baseline for the range in real-time data processing and display. Range engineers answered the X-29 program demands by developing the necessary capabilities in just 4 months. In the process, they created facsimiles of cockpit status panels on control room monitors. They established a real-time satellite link between the Dryden Range Control Room and the contractor's home base in New York. And they developed the capacity to deliver more than 4 million processed words per minute to control room display monitors and strip chart recorders on both sides of the continent in real time. The historic YF-12 also was a completely range-dependent test plane. This high-performance vehicle flew so fast and so high that no other airplane could stay with it. In a matter of moments, it covered so much territory that Dryden had to maintain an extended range in order to test it. As with the X-15, the Ely and Beatty test sites in Nevada became range boundaries for YF-12 experiments. Officially clocked at 2,000 miles per hour, the YF-12, with its air-breathing engines, was the prototype for hypersonic planes of the future. The National Aerospace Plane, or NASP, will be such a hypersonic plane, and much more. This is the next generation air and spacecraft. NASP will take off horizontally like an ordinary airplane, accelerate to escape velocity, leave the atmosphere, and fly in low Earth orbit. It'll re-enter the atmosphere and make a powered horizontal landing, again like an ordinary airplane. Currently in the design phase, this joint NASA Air Force research craft is targeted to make its first flight in 1994. NASP will take off and land at Edwards Air Force Base. As the program progresses, the plane will cover the continental United States in minutes. During flights in the atmosphere, range mission control will encompass every contiguous state. When NASP begins orbital flights, range scope will become worldwide. Telemetry will interface with NASA's tracking and data relay satellite system. NASP test flights may require multiple fully equipped mobile trailers positioned at strategic locations. Range controllers and researchers will need to know where the plane is every moment in terms of latitude, longitude, and altitude. At NASP speeds, this will be a major accomplishment. Researchers will need ground computer-processed instrumentation data during flights. This will place extraordinary demands on range acquisition and processing. Getting ready for next-generation test planes is a major challenge for range engineers. They're meeting it by developing next-generation equipment and support systems. A prime example is the Automated Flight Test Management System, or ATMS. This is a highly advanced, knowledge-based system being developed to assist researchers plan and conduct flight test missions and make necessary changes in real time. A flight engineer enters test parameters and aircraft performance characteristics, and ATMS provides an ordered set of flight test points. ATMS designers are experimenting with artificial intelligence to direct flight control programs. They anticipate big benefits for programs requiring the ability to record small changes in aircraft parameters during repeated maneuvers. From its earliest days, the Western Aeronautical Test Range has played a key role in advancing the latest concepts in air and spacecraft. The best aeronautical engineers have used its facilities to maximize their research. Milt Thompson is the chief engineer at Ames Dryden. Thompson was a test pilot on both the history-making X-15 and lifting body aircraft. He had a major part in creating the tradition of excellence here. He's among the few people qualified to give first-hand perspective on the development of today's aeronautics and the direction of tomorrow's research.
The key programs that kind of defined the range were the X-15 and subsequent to that the YF-12. That had an extremely long range requiring tracking, communications, and data relay. The NASA program will provide the next challenge for the range. It, of course, will be an extremely high-speed vehicle, potentially going on into orbit, and it will cover an awful lot of distance in its test program and during, say, an acceleration up to orbital speeds. And it'll require almost a worldwide capability, worldwide tracking capability to follow the vehicle in its development program. Any other program other than NASA that involves extremely high speeds will be candidates also for good utilization of the high range. For example, any scramjet or ramjet propulsion test programs. There again, the speeds will be high and it will require the support of a range such as what we currently have. These become essential, as I indicated, for safety to ensure that we know where the vehicle is and are able to guide the vehicle back to a successful landing. The range has been an essential part of the development of the high-speed aircraft. Without the range, I don't see how we could have done this. You have to have this tracking capability and the data transmission capability to really do a development program on these higher speed vehicles. In my opinion, there is just no question that we have an unsurpassed capability as far as being able to handle aeronautical research programs within this country and very likely within the world.
Building on its basic capabilities, television downlink including heads-up display, guidance and control uplink, worldwide tracking network ties, and transmission of data to any location, the Western Aeronautical Test Range undergoes continuous expansion, refinement, and improvement at the hands of its top professional engineers and support team. Since the time of the X-15, the range has experienced astounding transformations and expanded its capabilities to become the complex and indispensable network it is today. It will continue to be a vital resource for testing air and spacecraft of the future. Such future research craft, from exotic forms only now being familiar to those we have not yet imagined, will share a common link. They will depend on the Western Aeronautical Test Range, supporting exploration that knows no limit.